Good day for everyone. My name is Anastasiia Kiian, and now I would like to present you the results of our research on the topic non-binary constant way coding method. The presentation consists of several key points: motivation and state of the art, objectives, main part and results, and conclusions. Speaking about the relevance of the topic, it is worth noting that many applications are based on the binomial number system, including the so-called binomial codes used to increase the northern unity of binary asymmetric data transmission channels. Application of such codes is especially important in the context of code-based cryptography, which is one of the main approaches for implementation post-quantum cryptography. It should be noted that most applications only use binary constant way codes. We offer non-binary constant way coding technique. This will greatly expand the area of possible use of code-based cryptosystems. In particular, the use of such codes will increase the resistance of cryptosystems, which is especially important in the context of the development of quantum computers and accordingly new methods of cryptanalysis. So, the objective of the research is analysis of the well-known binomial binary constant way coding method, presentation of the basics of functioning of the new proposed method, and explaining of the possibilities of using new method and its advantages over an already known method. First of all, to further explain the proposed approach, it is necessary to understand the concepts of the positional and binomial number systems. The binomial system is based on the representation of numbers as increasing sequences of binomial coefficients. Thus, the number x in the binomial number system is represented as the sum of the products of the coefficient a by the corresponding binomial coefficient. The power of the constant way code, the number of elements in the set C, is determined by the number of binary vectors of length n and weight w, or in other words, number of combination of length n by weight w. For this case, system of code restrictions on the length of sequences of constant way, code world weights, and code cardinality are satisfied the following. A can be ranged from 0 to m, W can be ranged from 0 to n little n, and of course the certain coefficient way must be constant. So, for binary case, the number a is presented as binary sequence of constant way, and it should be noted that the considered technique doesn't imply the formation of non-binary sequences with constant way, and thus doesn't allow the implementation of non-binary constant way coding. In the proposed method, the number x is represented through an increasing sequence of binomial coefficients a with index I, where I is ranged from 0 to n, and corresponding sequence b with index I, where I is also ranged from 0 to n. A sequence A with indexes from 0 to w minus 1 and all its elements, non-zero elements of the sequence numbered according to the increasing digit orders, are formed using a positional number system on the base q minus 1. So, a set of non-zero elements defines the number that is represented in the positional number as follows, representing x with index p. The increasing sequence of binomial coefficients b sets a number which is represented in the binomial number system as x with index b. To present proposed algorithm, we need to use the following notation. N is a code length. C is a set of code words. The cardinality of non-binary constant way code is equal to m, which is determined by the following equation. And also we need to use the system of code restrictions for correct use of non-binary coding. A can be ranged from 0 to m. W can be ranged from 0 to little n, and the certain coefficient from the code world can be ranged from 0 to q. And of course, the way of the certain coefficient of code world must be constant. Let's consider the proposed algorithm for representing the numbers using the example of representing the number a. First of all, we need to represent number a in the form of numbers a with index b and a with index p, which were discussed earlier. The number a with index b can be ranged from 0 to q minus 1 to power w, and accordingly can be represented in the positional number system on the basis of q minus 1. Secondly, we need to represent the number a with index b in a binomial number system. It can be ranged from 0 to m divided by q minus 1 to power w and with code restrictions, as we can see on the screen. In case if we have a with index bi is equal to 0 for some I from 0 to n minus 1 in the a with index b representation, then we get the coefficient 0. In case when this coefficient is equal to 1, we get the coefficient is equal to a with index I. So the required element is equal to the corresponding non-zero element in the view of a with index p. These simple cyclic calculations allow us to get the final constant way sequence. As the next point, let's talk about advantages and applications of the proposed approach. The proposed number system allows complex use of both the local value of the digits of the code sequence and the values of binomial coefficients specified by the placement of non-zero elements of the sequence. Application of the developed number system allows us to build effective techniques and algorithms of non-binary constant way coding for their use in various practical applications. The proposed technique can be useful for improving post-quantum code-based cryptographic algorithms, ciphers, electronic digital signature, key encapsulation schemes, and pseudorandom number generators. Previously, it was mentioned that the use of constant way codes is one of the basic transformations of the functioning of code-based cryptosystems. In particular, constant way codes are used in the Niederreiter scheme. According to this scheme, an information sequence E that needs to be encrypted is converted using constant way codes into a sequence of fixed length is equal to n and constant way t. Then vector syndrome must be calculated. Decryption consists in removing the action of masking matrices, after which the sequence is decoded using a fast algebraic technique. The found error vector is a sequence of constant way E. Each possible information sequence should be uniquely associated with the corresponding constant way sequence. So, to build a code-based crypto system, it is necessary to implement an algebraic rule of this correspondence, implemented through a constant way count system. Thus, it is necessary to realize a one-to-one correspondence between all possible information sequences and various constant wave vectors. In the other words, for an arbitrary countable set, it is required to implement a new recording technique, number system, in the form of a set of constant wave vectors. At the moment, resistance versions of the constructions of code-based cryptosystems are based on the use of binary Gopa codes. In this simplest case, it is possible to use the well-known binomial count to convert information sequences into constant wave binary vectors. In the general case, code-based cryptosystems can be built for arbiter base, and for this general case we offer a generalized binomial positional number system and a new technique of non-binary constant wave coding. This will not only increase the strength of code-based cryptosystems, but also provide additional useful properties such as the control of non-binary errors during transmission. So, as a result of the research, a new number system based on the generalized binomial positional representation of numbers is proposed. It is that the complex use of the binomial counting system and the positional number system, the values of non-zero elements are specified through the local value of numbers. A well-known binary code is used to represent a number in the binomial number system. Non-zero elements of the resulting binomial sequence are additionally encoded with a positional code. The developed technique can be used in various practical applications, for example in code-based cryptosystems, ciphers, electronic digital signature, key encapsulation schemes, pseudorandom number generators, etc. Thank you for your attention.